This conference will now be recorded.
Very good evening, students. In the last class, we had learned about zeroth law of thermodynamics. So in zeroth law, actually it leads to the concept of temperature. Concept of temperature. So zeroth law of thermodynamics leads to the concept of temperature. Okay, that is what we had learned. And even before that, thermal properties of matter, in that chapter also we had learned the definition of heat and in fact the temperature. Temperature is actually the measure of temperature is measure of hotness, and it determines the direction of flow of heat. The direction of flow of heat. So up to now we know this thing. Today what we'll do, we'll get some understanding of heat, what is internal energy, what is work, and we'll learn about first law of thermodynamics. We had covered zeroth law of thermodynamics in the last class, which leads to the concept of temperature. Today we'll learn what is heat energy, what is internal energy, what is work, whether there is some difference between internal energy and heat energy. If there is any difference, what is that? And what is the difference between work done and heat energy? How heat energy is different and kinetic energy, work done is different from internal energy. So those things we'll be learning in detail, and we'll learn at the same time what is first law of thermodynamics. Okay. All right. So let us start with our today's discussion. First of all, we'll start with internal energy. Okay, we'll start with internal energy. What is internal energy? We'll define first what is internal energy. The internal energy, see, we have defined already that a thermodynamic system, thermodynamic system can have a large number of molecules. Okay, so suppose I have a container. In this container, this is kind of a piston. Generally we take a thermodynamic system. If the system is a gas, then generally we keep the gas in a container, cylindrical container with a piston. As and when required, the gas can do certain work, or maybe work can be done by surrounding on the gas. So this is the reason. Okay, suppose I have a gas. So gas has large number of molecules. And see, if this is not an ideal gas, then there will be mutual attraction, which is called mutual molecular force, mutual attractive forces between the molecules. This is called actually molecular force. So internal energy of a system means the total energy of a system. Like here the gas, total energy of the gas. So how many types of energy this gas can have, that is what I'm going to discuss. So if two molecules, they have internal molecular force or mutual attractive force, then working against this molecular force will give rise to a stored energy that is called molecular potential energy. So a system can have a potential energy. Okay, a system can have potential energy. A system can have potential energy. You understand now that, like, see, if we have like real gases, they have mutual attractive forces. When we work on, like, see, if we just compress the volume of the gas, we have to do certain work against this gas mutual attractive force. Okay, or if we expand, then also, if we expand, then gas is doing certain work. So this work done actually is stored in the gas as potential energy. So we have potential energy. Not only that, see, these molecules can vibrate with a common center. So they have vibrational kinetic energy. So they have kinetic energy and potential energy. Kinetic energy, how kinetic energy will arise? Because the gas molecules are not at rest. If you see, even though the system is at rest, the center of mass of this system is at rest. This you have to understand. COM, center of mass of the system is at rest. Of the system is at rest. But still, the gas molecules, they are actually randomly moving. So because of this random motion, you have kinetic energy of the system. So gas has kinetic energy. How many types of kinetic energy it can have? Translational kinetic energy, kinetic energy. It can have vibrational kinetic energy, and it can have rotational kinetic energy. Okay. So now you can understand, or you can guess, what do you mean by internal energy. It is the total energy of the system. It is the total energy. Total energy means this potential energy plus these three types of kinetic energy. So then how do we define internal energy? Let us define internal energy now. So I have told you that a system can have large number of molecules, so they can have internal molecular forces. So we have to do certain work against those forces that will store as potential energy. So the internal energy of a system is the sum of the molecular kinetic and potential energies internal energy of a system of a thermodynamic system. Of a thermodynamic system is the sum of molecular kinetic and potential energies I'll erase this portion. In the frame of reference, so that internal energy of a thermodynamic system is the sum of molecular kinetic and potential energies in the frame of reference. Frame of reference. Frame of reference in which frame of reference relative to which the center of mass of the system is at rest. This I have discussed already. The center of mass of the system. The center of mass of the system is at rest. Okay. So this is the definition of internal energy. Now this definition is not enough. We have to learn much more details of internal energy. Let us see what are the properties of internal energy. There are various properties of internal energy. We'll learn those things and try to understand what each term means. Okay, so if we understand what is internal energy properly, then it is easy to understand the concept of heat, work, and first law of thermodynamics. Okay, so now discuss properties of internal energy. The internal energy of the system is a thermodynamic state variable. So let me write properties of thermodynamic. Okay, properties of internal. So as you know, like in mechanics generally, we denote potential energy as PE or sometime E suffix P, and kinetic energy sometime we write K dot E or sometime EK, etc. we write. Similarly, the internal energy of a thermodynamic system is denoted by capital U or sometimes small u. Okay, so internal energy is denoted by U. Okay, caps U or small letter U as okay U. So you have to understand that U in thermodynamics means internal energy. So this internal energy I'm writing now as U. U is a Is it audible now? Is it audible, madam, now? I hope it is audible.
Yes, yes, now I can hear. Previously, I can't hear you, Ram.
How long didn't you hear me, madam? Like
2 minutes,
how long? 2 minutes.
Two,
So
yes.
do I? Okay, no problem. 2 minutes. I was discussing this internal energy only. All right. So
Oh,
okay. So dear students, if you have not heard this last 2 minutes, just hear now. The internal energy is the sum of, as I was discussing, that a thermodynamic system can have large number of molecules. They can have molecular forces between them. So there will be, if there is some internal forces, so there will be potential energy involved in it. And gas molecules are always moving randomly here and there. Okay, so that's why there are kinetic energies and potential energy. And I had mentioned potential kinetic energy can be of three types: translational, rotational, and vibrational kinetic energy. Okay, and so we have just written the definition. The internal energy of a thermodynamic system is the sum of molecules, sum of molecular kinetic and potential energies in the frame of reference relative to which the center of mass of the system is at rest. Okay, I was telling you this also. Okay, now we'll discuss some properties in detail so that you can understand what is actually internal energy. So now we are discussing some properties of internal energy, and internal energy is generally denoted by U, capital U. Okay, caps U. So this is U. You should understand this is U. Okay. So when I write in thermodynamics, whether it is small u or capital U, you should understand this is internal energy. Okay. So internal energy is a state variable of a thermodynamic system. Is a state variable of a system. System means thermodynamic system. So you know the value of internal energy does not depend on any other factor. Other factor means, I'll tell you, it does not depend on path or the means how a particular state of a thermodynamic state has been arrived is not important. I'll tell you this thing. See, how do we define a state? How do we define a state of a thermodynamic system? Of thermodynamics system. Actually, state of a thermodynamic system is specified by pressure. Okay, pressure, by its volume and temperature. These are the factors. If you define a state of a system, you have to specify what is the pressure, what pressure is denoted by P, what is the volume denoted by capital B, what is the temperature denoted by T. So P, V, T. So these three things you have to tell if you want to specify the state of a particular thermodynamic system. So if I know that a particular thermodynamic system is at a state of P1, V1, and T1, like at a state where the temperature, pressure, and volumes are like this: P1, V1, and T1. So this state has a certain internal energy, suppose U1. Now, if we change somehow the state of the system to P2, V2, and T2, then it will have some other potential energy, sorry, other internal energy, that is suppose U2, U2. This U1 and U2, these are not same, because this potential, see, this internal energy depends on the state. U1 is the internal energy associated with the system when the states of the system is defined as or specified by P1, V1, and T1. Then internal energy is U1, and the internal energy U2 is associated with the state which is specified by the pressure P2, volume V2, and temperature T2. So these are two different states of the system. Then it has two, these internal energies are different, but this internal energies U1 and U2, this is just due to due to the states, due to different states, but it does not depend how you arrive this system from P1, V1, T1 to P2, V2, T2. It is not the business of internal energy to know whether, like, how it arrives to other systems, other states. I'll just give you certain example. I'll just explain you what is state variable properly. So state variable means it depends on the states. That means it depends on the P value of PVT. Okay, pressure, volume, and temperature. Okay, so it is a state variable. I'll just make you this concept little more clear. Suppose I have the same example I am taking. Suppose I have gas, okay, which has pressure P1, volume V1, and temperature T1. Now it has internal energy U1. Okay. Now suppose I am just changing the state of the system, to P2, V2, and T2. Then it has internal energy U2. Okay. Look, I can arrive to this state from this state in three different ways, at least two. Let me do one thing. So what we can do, we have to change the pressure and temperature and volume. Pressure, temperature, volume, all three I have to change, suppose. Okay. So if I keep the pressure constant, then see intermediate states, I can write this, suppose this is intermediate, some intermediate states, I can keep the pressure constant, change the volume. Okay, and let us do it isothermally, so the temperature also remains the same. At this state, you know, the internal energy remains the same anyway, because the temperatures are same. Now I'll keep these two constant at this stage. Temperature can be changed, so I'm not drawing this. Now I have the state P1, V2, and T2. I have changed it to T2. I have kept the pressure constant. Then I'm finally changing the pressure also. So P2, V2, and T2. See, this state can be again like changed in another way also. Suppose I go to next. I can go from P1, V1, T1 to first P2, then V1, T1. Then I can change pressure and temperature, keeping the volume same. Then finally I can change the volume keeping both temperature and pressure constant. Kind of this I can do. So I can do in two ways. Even I can do in several ways. Okay, but it does not depend on how I do arrive from P1 V1 T1 to P2 V2 T2. Rather, it depends on the final state. If we arrive to final state P2 V2 T2 in both cases, see in this way also I'll have the internal energy U2 at last, and here also we'll have internal energy U2. Both ways it will be the same. That means it does not depend on the path or the means it is achieving the state. So I'll okay. So first is U is a state variable. State variable. So this we have understood. Now second point is, so for an internal, sorry, for an ideal gas. See, for an ideal gas there will be no molecular force. For an ideal gas, no molecular force. Intermolecular force. Okay, we should write intermolecular force. Molecular force. No internal molecular force. So there will be no potential energy. So potential energy will be zero. So in that case, for ideal gas, so for ideal gas, the internal energy is purely kinetic energy. That may be sum of translational, vibrational, and rotational. So we can write that for ideal gas, for an ideal gas, the internal energy that is U is purely kinetic energy. Purely kinetic energy. Okay. So now, so these are few things which you need to know. And like, see, kinetic energy, when I am talking about kinetic energy, another thing is that for ideal gas, for an ideal gas, U actually it is U is, or internal energy is directly proportional to temperature. Directly proportional to temperature. Okay, directly proportional to temperature. How? If temperature is more, then the random motion will be more. If temperature is more, vibration will be more. Okay, if temperature is more, then rotation also will be more. So translation, vibration, and rotation all will be increasing if the temperature is increased. Okay, so internal energy for an ideal gas is directly proportional to temperature. Okay, now the question is how to change internal energy of the system. So there are two ways. Look here in this figure. Suppose I have a system of gas. So these are the gas molecules, as you say. See, this is the piston. This is actually a movable piston. Movable piston. Okay, movable piston. And see, this is a source of heat. So you look, when the temperature is increased, then internal energy will be changed, as I said. internal energy is directly proportional to temperature. So how do you change the temperature? If suppose you keep the system in a surroundings which has greater temperature, suppose this has T2 temperature surrounding and this has gas has temperature T1. If suppose T2 is greater than T1, then what will happen? There will be heat flow. Heat flow will be there, and there will be heat like or energy flow. Heat energy flow will be there to the system. And if the system takes up energy from heat energy from surroundings, the temperature will rise. So internal energy will change or it will increase. It can be either way also. If suppose the temperature of the surrounding is less than the temperature of the system, then what will happen? Heat flow will be happening in the reverse direction. That means heat energy will flow from the system to the surroundings. Okay, and then you know what will happen? Temperature will be gradually decreasing because the heat energy is lost. Energy is lost, so temperature will decrease. Therefore, the internal energy will be decreasing. So this is how internal energy can be changed. Okay, so one way we have got by supplying heat energy, and another way is there, that is, see this movable piston. If suppose applying certain pressure, the movable piston is moved inward so that the gas is compressed. If the gas is compressed, then surrounding is doing certain work on the gas. Surroundings doing certain work. Doing work on the system. If work is done on the system, then what will happen? Then also internal energy will increase. Then also internal energy will increase. Okay. Then also internal energy will increase. Further, it can happen in the reverse way also. If the gas is doing certain work on the surrounding, then internal energy will be decreasing. So compressing means internal energy getting increased, or if the gas is expanded or expanding by itself, then it is doing certain work on the surroundings, so the internal energy will decrease. So thus we can see that by moving the piston or by doing certain work, internal energy is increased or decreased. So there are two ways then. One is work and another one is supplying heat energy. So when the heat energy is supplied, its molecules become faster in all directions. They move faster in all directions. So the heat energy, then heat energy is what? Heat energy. So you can understand heat energy and internal energy, both are energy, but both are not of same kind. So heat energy is energy in tangent. Heat energy is an energy in tangent. So it can only transfer from one body to another, colder body, hotter body to colder. Okay. So heat energy is an energy in transit. Heat energy, so you can understand what is the difference between heat energy and internal energy. So heat energy can transfer from one body to another. Okay, this transfer of heat actually produces randomness. If the heat is transferred from surrounding to this, so more randomness, so more internal energy. Or if the heat energy is released by the system to the surrounding, then randomness will be decreasing, so the less internal energy. So heat energy can be transferred from one body to another. That depends on temperature, from which body to which it will, whether it is heat energy will be transferred from system to surrounding or surrounding to system. That will be determined by the temperature of both the system and the surroundings. In fact, the temperature difference between these two. Okay, now when the piston is compressed, a gas has to do certain work. The piston is doing certain work, and it forces, like gas molecules will force against this motion of the piston. In fact, what may be regarded as one mode of energy, work also may be, since work is actually increasing or decreasing, work is actually influencing the internal energy. So work also can be regarded as work also can be regarded as the mode of energy transfer. Heat is also the mode of energy transfer, and the work is also the mode of energy transfer. So these are very, very important concept, and very subtle difference is there. Energy transfer that produces organized motion. So that produces organized motion. I'll tell you what is this saying. See, when work is done, suppose piston will come towards, like inward, then see gas molecules will not be becoming that random. They will actually move with the piston. So this is called organized motion. Initially they will be in random motion, but as the piston is like volume is decreased or the gas is compressed, then molecules will be more organized. So this is, so work done is an way, work done can be regarded as the mode of transfer of energy that produces organized motion. Okay, so these are few points. Now we'll see basic difference between heat and internal energy. So this I have already told you there. So both are energy. Heat energy does not specify, or we should say cannot specify the state of a system. Heat energy cannot specify the state of a thermodynamic system. State of a thermodynamic system. Okay, whereas internal energy uh, is a state variable. Okay, it is a state variable. Okay, so heat energy is a mode of transfer of energy. Heat energy is a mode of transfer of energy. So this is one point. Okay, heat energy is a mode of transfer of energy. Heat energy is a mode of transfer of energy. Transfer of energy. Okay. It in fact depends on temperature. Okay. And it is not a state variable. State variable. It depends on, see, I'll tell you one more thing. So the internal energy, which is a state variable, this is denoted by or defined by or specified by PVT. But Q is the heat energy. Suppose it is not a state variable. Okay, it depends on path. Then it depends on path. How you go from one state to another. It depends on path. Or means it does not depend on path. Does not depend on path. You might be wondering what is this path. Suppose you are going one state P1 V1, from P1 to P1 V1 T1 to you are going to some other state P2 V2 T2 of a system. The heat energy depends on the path, like how you change P1 V1 T1 to P2 V2 T2, but it does not depend on the final. Not only it does not only depend on the initial and final state. Whereas this internal energy, since it is a state variable, it depends only on the initial and final state. It doesn't depend on the intermediate path what you take. Okay, so these are few basic difference between. So actually, since it is not a state variable, heat is not a state variable, we cannot say a system has certain amount of heat. Rather, we can say a system has certain amount of internal energy. So that we can say. So we can say that the sentence that a system is supplied certain amount of heat energy so that it increases the internal energy or something like that. That we can say. So heat always is used to heat energy is always used to like give a supply or transfer from one system to another. It does not specify state of any system. Now we'll see some basic difference between heat energy and work. Actually, heat is also a mode of transfer of energy, and actually heat, both are mode of transfer of energy, but heat actually depends on temperature. Depends on temperature difference. Temperature difference, okay? Temperature difference. Okay, but work is denoted by W, does not depend on the temperature difference. Does not depend on temperature difference, okay, between two systems. So yes, so this is the difference, okay? So actually heat energy produces random motion because it will help to increase the internal energy, and work produces more organized motion of the molecules. More organized motion, okay? Now excuse me, I'll go further 10 minutes. We'll now learn the sign convention to take, like when we measure the heat or internal energy or temperature, how do we take like whether heat energy is negative or positive, how to define when to take positive, when to take negative. Similarly, how to take work positive or negative, how to take U positive or negative. This actually there are some common sense. Based on common sense, there are certain law or convention, not law, certain conventions. So heat absorbed by a system is positive. Whenever heat absorbed, sorry, whenever we say heat is absorbed by a system, that has to be taken, heat absorbed has to be taken positive. Then if we say heat released by a system, heat is heat released by a system, then we have to take negative. Okay, this is with heat. Now we'll see with work. So work done is positive when the work work done by a system. Work done by a system is positive. Work done by a system is taken to be positive. Then work done on the system is taken as negative. Okay. Now internal energy, increase in internal energy of a system is taken as positive. Increase in internal energy is taken as positive. Increase in internal energy is taken as positive. Decrease in internal energy is taken as negative. Okay, so these are the things. Now we'll discuss briefly about first law of thermodynamics. Okay, so or else we'll start. It is already going to be 4:30. Sorry, 5:30. I'll take another 5 minutes to start with the first law of thermodynamics. Then we'll discuss in detail later. So first law of thermodynamics actually is the conservation of energy. So it is the outcome of conservation of energy. We have learned law of conservation of energy, and many times we have used also to find out answer for various problems. So first law of thermodynamics, we will just have introduction for today, and details we'll discuss in the next class. So it is simply the law of conservation of energy. The law of conservation of energy. Applied to any system in which energy transfer happens from or to surroundings. Okay, so it is simply the law of conservation of energy. So in this case, actually, conservation of energy. See, in case of like other mechanical system, what happens? So kinetic energy gets converted to potential energy, or potential energy gets converted to kinetic energy, and the total energy will be always conserved. So kind of that. So in this case, actually, see, not the kinetic energy and potential energy. We'll see now in terms of the heat energy, the work, and internal energy. These three parameters. Okay, these three parameters. If some heat is supplied, so the statement of this first law of thermodynamics is that if if some heat is supplied to a system, if some heat is supplied heat is supplied to a system, is supplied to a system. So this is actually according to first law of thermodynamics. The first law of thermodynamics if some heat is supplied to a system capable of doing work, okay, capable of doing work, capable of doing work, then the quantity of heat absorbed, then the quantity of heat absorbed by the system will be by the system will be the sum will be equal to the sum of the increase in internal energy and external work done by the system and external work done by the system on the surroundings. I'll explain you that. Okay, so according to first law of thermodynamics, if some system is supplied a certain amount of heat energy which is capable of doing certain work, then the quantity of heat absorbed by the system will be equal to the sum of the increase in internal energy and external work done by the system on the surroundings. Let me explain now. See, suppose the heat supplied is this one, dq heat supplied, okay, then change in internal energy is denoted by du delta u. In fact, this is called del u del q. So del q and del u, and this is the work done by the system on the surroundings. Then, according to first law of thermodynamics, this dq, the heat absorbed by the system, will be equal to the sum of the internal energy, change in the internal energy, and the work done. Work done, I hope work done. Okay, let me write as dw itself. So this is the statement in mathematical form. So we'll stop it here. So we are just uh, ending the class with this statement itself. Next day we'll discuss in detail what is like how do we express this work done. Work done can be expressed as P delta V. Okay, this will explain again. Okay, if some cases change in the internal energy is 0, then the whole heat absorbed will be equal to work done by the system. So these are the things we will discuss again. Today we'll stop it here. Okay, thank you. Bye for today.